Hi, good morning. I want to start thanking the meeting organizers for inviting me to give this presentation. I'm going to talk about free surface flows of particle suspensions. So many liquids that are used in different manufacturing processes are non-Newtonian. So in many coating and extrusion applications, the liquid has particles suspended, particles of different shapes and different sizes. So depending on the size of the particles, the non-Newtonian behavior of the liquid can be very different. So you can have very strong shear thinning behavior, or even at high concentration, shear thickening behavior at very high shear rates. So typically the rheological behavior of these fluids is a function of the concentration and of the shear rate. And typically, if you're going to do a simulation of this process, you assume that the particle concentration is uniform in the flow. And then you get your rheological behavior from that particle concentration. And the viscosity or other rheological properties will vary with the local shear rate. However, shear-induced diffusion may lead to very non-uniform particle distribution within the flow. So you may have regions where the concentration of the particles is below the bulk or the average concentration, and you may have regions where the particle concentration is much higher than the average concentration. And moreover, this particle distribution and particle orientation in the case of non-spherical particle may affect the functionality of the product that you're manufacturing. So these are the goals of our study. So as I mentioned before, the flow behavior has a strong effect on both the particle distribution and particle orientation. So here are two highlights from the literature showing evidence of this phenomenon. So here we have the Poiseuille flow between two parallel plates of a particle suspension. And you can clearly see you have a higher particle concentration away from the walls in the region of zero shear stress or shear rate. And in this another example here, we are looking at the flow of elongated particles through a convergent divergent channel. And you can see that the particles are aligned in the orientation of extension. So in the contraction part of the channel, you have a uniaxial extension. So the particles are aligned within the flow direction. And then in the divergence part, the particles are aligned perpendicular to the flow direction because you have a biaxial extension. So we need to have an accurate models that take these effects into account. So whenever you're going to study a problem like this, you need to take into account that the rheological behavior in a region near the wall will have a local particle concentration smaller than the bulk, and then that may affect the shear viscosity and other rheological properties of the flow. So as I mentioned, the goal is to study process flows of particle suspension and look at the effect of the flow parameters both in the particle distribution and in the orientation. And maybe that these type of predictions may help to understand how the microstructure or a final performance of the product that you're manufacturing can be controlled by the process conditions. So the mathematical formulation is explained in the next slides. So typically in the process that we are going to focus on, Reynolds number is fairly small. Stokes number is also fairly small. So we combine incompressible mass conservation equation, a momentum transport. In this example that I'm showing here, we are neglecting inertia, but we can include inertia in the model. And what's different now is that we have a particle transport equation. So there's going to be an extra field of a particle concentration that will vary with position. So we have a convective transport of the particle and then a diffusive term. And this diffusive term, these different diffusive flux are going to be associated with the flow. So this is like a flow-induced diffusion. And we include different parts of this total diffusion flux. One is associated with the different gradient of frequency of collision of particles. So if particles will move from regions of high collision frequencies to regions of low collision frequencies. And these collision frequencies are directly associated with the local shear rate. So particles will migrate from regions of high shear rate to regions of low shear rate. That's why in the example I showed you in the beginning, that you had particles concentrated in the middle in between the two parallel plates and a lower particle concentration near the walls. There's another term of the total flux associated with the spatial variation of the viscosity. If I have a collision of two particles, the particle that's moving towards the region of lower viscosity will move faster So there is a net flux of particles going to this region of lower viscosity. And there are other terms associated with the framing variant formulation. And we can include also sedimentation if the particle doesn't have the same density of the suspending liquid. We are going to assume that the liquid stress is composed of these three parts. So the regular isotropic part of the stress, the viscous stress, we're going to make the local viscosity a function not only of the shear rate, as in a shear thinning liquid, but also a function of the local particle concentration. Okay, so the viscosity, so we need to find the local particle concentration at each point of our flow to go and look at the viscosity as a function of the particle concentration and also of the shear rate. If we have spherical particles, we only have these two terms in the total stress. But if the particles are elongated, there's an extra stress associated with the particle orientation. Okay, so this extra stress is given by this term here, where m is the particle conformation tensor. So it gives the direction of the particle. And then when we do this double dot product with the deformation rate tensor, we are looking at how the particles is aligned or not with the flow directions. So we need an extra equation for non-spherical particles that will tell how this orientation is transported. So how this particle conformation is transported. Again, we have a convective term and a particle orientation term. So the particle will tend to align with the extension direction of the flow, that as I showed you in the beginning of the talk. And there's a particle relaxation. So if this flow stops, the particle will go to a random orientation, and it takes some time to get to this random distribution of orientation. And this is characterized by this characteristic relaxation time lambda. So at the end, we have the unknowns of the problem, the velocity and the pressure field, the particle concentration, the particle orientation if we are solving for non-spherical particles, and the free surface configuration in the case of free surface flows. That's going to be one of the examples that we're going to look at here. So we solve this using finite element method. In the case of free surface flows, we map the unknown physical domain to a known reference domain. So we need to solve an extra set of differential equations that governs or describe this mapping. So we couple everything and solve it a fully coupled system, okay? And we use Newton's method to find the solution of this non-linear problem. So I'm gonna go through some of the results here. The first one is a simple flow, just a flow through a constriction channel. On the left here, I'm showing the particle distribution. We can clearly see that as the flow, as the liquid goes through the constriction zone where the shear rate is higher, is stronger, the particle concentration near the walls gets to be very small. So particles are diffusing away from the region of high shear rate towards the region of low shear rate. That's why we get this region of very high particle concentration at the symmetry axis of this flow, okay, as similar to the experiments I showed you before. And on the right here, I'm showing particle orientation. So we can clearly see again, when we get into the convergent part of the channel, the particles are aligned with the flow. This theta is close to 0, where theta is the angle with the horizontal direction of this plot. And as we move towards the divergent part of the channel, you can clearly see that the particles achieve an angle close to 90 degrees. So again, the particles are oriented perpendicular to the flow, but in the direction of the biaxial extension. And this qualitatively reproduce the experimental results that I mentioned before. So we can see that the model is capturing the basic physical phenomena of shear-induced diffusion and also extension orientation of the particles. So the other example that we are looking at is the extruded swell flow. So there are some results in the literature that shows that if you have a liquid with particles suspended on it, the dye swell phenomena is very different. So here's an example of a polypropylene dye swell. So here's in this red circle would be the diameter of the slot of the capillary where this is being extruded from, and you can clearly see the extruded part is much higher than the orifice diameter. But now if you have particles filling up this polypropylene solution, you see that there's no extruded swell. There's actually a contraction of the material. So there's a lot of studies trying to relate this phenomena to the change in the rheological properties associated with having the particles suspended in the polypropylene solution. And we are going to show that maybe this phenomena can be explained by this particle migration effect that we've been discussing here. So here I'm showing the particle distribution for a very low particle concentration, so 10% only. You see, so this is a capillary flows. This is where the capillary ends, and from this point on, you have a free surface flow. So as the liquid is flowing through the capillary, there's a region of high shear rate near the wall. So particle will diffuse towards the symmetry axis. So that's where you get this higher particle concentration. At only 10% particle concentration, the effect is not very strong. You get to a maximum particle concentration around 35%. But now if you increase the bulk concentration to 40%, this becomes a stronger effect, because now you have more particles colliding with each other. And you can clearly see that particles move away from the wall towards the symmetry axis again. And the particle concentration in the symmetry axis can be very high. So here, remember, the bulk concentration is around 40%, and we have a concentration here at the symmetry axis close to 60%. So the viscosity, the local viscosity at this point gets very high. So this is completely changed the flow dynamics, because now I have a very high viscosity liquid here near the symmetry axis and a lower viscosity liquid near the walls. So in a sense, you have like a lubricating layer near the wall. And you can clearly see that with this low particle concentration, we see the exudate swell. So the diameter of the exudate is higher than the diameter of the capillary. But in this case, with the 40% particle concentration, there's a contraction of the exudate. The diameter of the exudate is smaller than the diameter of the capillary. So here, just considering this local change of particle concentration can explain this phenomena of exudate swell or exudate contraction. And what's happening is that I'm showing here the velocity as a function of position. So for the Newtonian liquid, you have a high velocity in the capillary. As soon as the liquid goes out of the capillary to the free surface flows, you see that, and then you're going to move towards a plug flow. The velocity at the center line has to decrease. So you have this velocity jump. But now if you have a higher concentration, remember the viscosity near the symmetry line becomes very high. So it's very hard to decelerate the liquid. So the change in the velocity in the symmetry line is much smaller. So you have a lower normal stress associated with the flow of a high particle concentration. And this lower normal stress leads to lower swell, and in some cases, even a contraction. So this is what I'm showing in this plot here, where I'm showing the profile of the free surface for a Newtonian liquid, where you see an exudate swell a little bit more than 10%. And as you increase the particle concentration, the exudate swell becomes weaker and weaker. And then we go to a particle concentration of 40%, you see that there is an appreciable contraction of the exudate. So again, these predictions, they agree with the experimental data, and maybe they can show even with the Newtonian behavior that we are assuming here, you can completely remove the exudate swell just by this considering the non-uniform particle distribution within the flow. So this, the other example is a slot coating flow. So slot coating is used in the manufacturing of many functional films. Again, if we have a particle suspensions flowing in the slot die, in the feed slot, you get this particle concentration, because again, this is a Poiseuille flow. I have two parallel plates. I have a pressure-driven flow. So the particles will move towards the region of low shear rate. In this case, the thickness is half of the gap. So this ratio gap over thickness is equal to 2. So it means that we have almost a pure co-ed flow between the downstream dyed lip and the moving web. So there's no gradient on the shear stress because it's a co-ed flow. So the shear rate is constant. So there's no shear-driven diffusion. So the high concentration regions gets convected. Then you have this particle distribution where you have a higher concentration near the film. However, if we change the flow rate, so if we reduce the flow rate to coat a thinner layer, so now in this case, here's a gap over thickness of 4. You have a combination of a co-ed and a pressure-driven flow in between the downstream dyed lip and the moving substrate. And there's a region of low shear rate near the dye lip. So you can see that this region of low shear rate is where the particles are accumulated. So you have a region of very high particle concentration in this recirculation zone that appears. And this may have a very strong effect in the flow. It has been seen in the literature that as the particle, if you have a high concentration particle suspension, it's very hard to coat thin films without having streaks. What happens is that the particle concentration can get very high in this recirculation zone. And as the particle concentration is getting high, they can agglomerate and form agglomerates that may get stick to the dye surface, and that will lead to streaks in the coated film. So this simulation again can explain some of these streaking phenomena observed experimentally. Here's just an example of particle alignment within the flow in slot coating. And just to highlight the main result here is that as we reduce the film thickness, going from a gap to thickness ratio of 2 to 4, so I have a thinner film, it means that I have a stronger extensional flow. So this stronger extensional flow aligns the particle, and then I have a film that's formed here with almost 100% of the film have particles that are aligned within the flow. So maybe that's a way of trying to, if you're trying to get a product that your particles need to be aligned within the flow, considering what's the optimum process conditions may help you. So as final remarks, we see that these free surface flows are strongly affected by the suspended particles. The non-uniform distribution of particle within the flow may have very strong effect on the flow behavior. But we need to make sure that the models are capturing all the relevant physical phenomena. So in a sense, we need experimental verification of these complex models that I'm showing. So this is work in progress. We are trying to visualize these particle suspension flow. It's a very complex experiment because a liquid with particle suspensions, with particles suspended on it, is very hard to visualize away from the boundaries. This is typically a fairly fast flow, so it's again hard to visualize. And the presence of free surface makes visualization very challenging. So we are using a confocal microscope to be able to go inside the flow and visualize the dynamics of the particles away from the boundaries. And we are using a fast resonance scanner in order to be able to achieve this, to look at these fast dynamics. So here's an example of another application that we used confocal microscope that was published a couple of years ago. This is not associated with particle suspension flow, but we are looking at the displacement of two liquids in a porous media. But you can see that the acquisition rate is fast enough that we can capture this dynamic behavior. And this is the same thing that we're going to use here for the particle suspension. So we are going to try to get experimental data for the first problem that I showed you results, where I have a particle suspension flowing through a constricted capillary. So we're going to vary the geometry of the capillary, and we're going to use polystyrene particles with a diameter of 6 micrometers. They're going to be fluorescent, so we can see them in the confocal microscope. So as I mentioned, it's a fast scanner frequency, so we are using a 12,000 hertz frequency in order to be able to get the image of the plane that we are looking at fast enough that we can capture these dynamic features of the flow. So we have to go through a lot of process in terms of image processing, going with different filters and then identification of the particles and then algorithms to count the concentration of particles in different regions of the flow. So here's some preliminary results where we are looking at the particle distribution within the cross-section of the capillary. So the blue distribution is before the constriction. You can see that we have a higher particle concentration in the center and lower particle concentration near the walls as we expected. As the flow passes through the constriction where there is a higher shear rate gradient, the particles will tend to migrate towards the center. And then if we look at it after the constriction here, you see that the particle concentration in the center line after the constriction is a little bit higher than the particle concentration before the constriction. The change was not very high because we are still in a very low particle concentration here. I think in this example was around 10%. So we need to go to higher particle loading, but again, the experiments become much complex. And also we are planning in the future to repeat these experiments, but not with spherical particles, with elongated particles. And we want to see if we can visualize this alignment effect of particles in the converging section being aligned with the flow, and in the divergent section being aligned perpendicular to the flow. So I'd like to thank you for your attention. Please send emails if you have any questions later on. And whenever life comes back to normal, I would like to welcome to visit PUC-Rio in Rio de Janeiro. Thank you very much for your attention.